Okay, everyone, I'm just going to run through some examples really quick, and you'll probably have a few different videos for this chapter too. Oops. Okay, and this one we are going to be doing work across a moving boundary. Okay. So this is like the type that we're doing in case you have similar questions. So here is our, given a frictionless piston cylinder device which contains water vapor. And here's our givens. 10-pound mass, pressure 60 psi, and then temp of 320 degrees Fahrenheit. Okay, and some additional information is piston is not attached to a shaft. Okay, so let's draw it. Right here, it's not attached to a shaft. It's right there. Here's our system. Okay, this is water vapor. And it has a temperature, so we know that we have some heat down here. And it's telling us to find work between 1 and 2. Okay, so we know that right here it's a frictionless piston cylinder device and it contains water vapor. So we've got that. We've got some givens right here. And it also says that the piston is not attached to a shaft. So we know that from chapter 1 and working on in chapter 3 that we can do our forces. So we've got atmospheric force pushing down, we've got the weight of the piston pushing down, and then we've got water vapor pushing up. And so we know that we can do the sum of forces here in the y direction. So we've got a negative atmospheric force, we've got a negative weight of the piston, and we've got the water vapor. I'm just going to denote it as W. Water equal to 0. And then, so if we're looking for work between 1 and 2, we would need to know what our system is doing, right? So let's isolate our system, which would be the force of the water. Remember, you can break these down. I'm not going to break them all down here. I'm just going to write it out. By pressure of the water times area of the piston. You know that weight gets into mass and gravity, and then again, this is pressure and area. But I do want to note that these are constant. And so then we can just move this to the other side because that's what we're trying to identify. It's kind of what we're working with here. And since we know that these equal constant, then we can rewrite this as pressure of the water times area of the piston equals constant. Okay, so this is important to know. Okay, and then we can start working on the solution. So if you need to take a moment and kind of write this down, I'm going to start a new page. Let's see. Okay. So let me write down our solutions. Right? Okay. And so we know that we have this formula from the lecture. You've seen it. And I said that we would be working some examples. So volume 2, volume 1, P, D, V. And we know again, pressure is constant. So what can we drop this down for? 1, 2 equals. So we can pull out P out of the integral because it's constant. So it's going to help us solve this. 1, and then dV, which then equals P when you solve this, V1. And this is why I said, hey, in the lecture, it's good to go ahead and work through solving these. And just a note about V, we don't know anything about V, right? V, total volume, but we do know that whatever this total volume is, we can get specific volume from, right? And we do know this. Let's just put known. Perfect. Okay. And then we know that we can use the tables to find this. So then we would just end up rewriting this because we know this and we know this, so therefore we can get this, right? So then we would just end up with that. So again, let's just drop this down here. And then that goes to so we've got this formula right here because we can get these two. So we're just going to plug them in here. So V2 times mass is constant, minus V1 times the mass. And then again, to just simplify all of this, we can pull out the m's because we can pull them out here and put them in front. V2 minus V1. Okay, so now we have something that we can work with, right? Because we know that we started out with this and we needed to get some digits from that. We used the sum of forces to help us out with that, to help get some of this out. We were able to get pressure. And then again, well, what can we do further? Well, we have total volume. We don't know what total volume is, but we do know that we can get specific volume from the tables, and we do know the mass. So therefore, we can find it out through using this information. And then you just keep simplifying it until you get to a formula that you can really work with. So let's start applying this, right? So we are going to do this the way that we've been doing it the whole time, but we're just now adding in more steps. So at state 1, we first identify V. So how do we do that? Assume a two-phase mixture, which is table A3E, YE, EE units. Remember whatever table that you're working with. A3, if you need it in EE units, it'll have an E at the end. And so then, since we are given pressure, so at a pressure of 60 psi and a temperature of 320 degrees Fahrenheit, we know that this, our Tsat, is 292.73 degrees Fahrenheit. And then, so with this information right here, we can go to the flow chart. And that state is superheated vapor. Okay, and then where do we go from there? We go to table A4E, because we're still in EE units, and then at P equals 60 psi and a T of 320 degrees Fahrenheit, we're looking, and what we end up finding out is that because this value is in between two values, what do we need to do? Because we've been doing this a couple times, we need to interpolate. At P equals 60 psi. And so then that pulls to, let's see, trying to help you out. Okay, so T equals 300 degrees Fahrenheit. I'm skipping moving through the tables because you guys have had a lot of practice on that. But if you're still having trouble, just email me, and I can even just send you an example. But we've worked through all of this, so if you do need a refresher, you can, of course, go right back to the previous videos. But you should be able to pretty well follow along and know what I'm doing. I'm just trying to save time. Okay, so we know that our value is in between here, and we're trying to find our V at 320 degrees Fahrenheit. So we are going to interpolate, let's see, 7.26 feet cubed pound. We don't know this, we're trying to get this. 7.82 feet cubed pound. And then when we plug this into the formula, remember it's really easy to set up your formula like this so that you know exactly where those values need to go. It ends up looking a bit like this. Over minus 300, and then 320 minus 300, and then that, when you solve it, ends up with a specific volume of, ends up with a specific volume of 7.485 feet cubed pound, and this is specific. Okay, volume at state 1. Okay, so we have that information, and then what can we do? We can go into state 2. Okay, and then at state 2, P1 equals P2 equals 60 psi. Why? Because we know that pressure is constant. And then T, 400 degrees. I think I forgot to add, let's see, let's go back. Did I add this portion? Let's see if I can get back to it, if it's going to load. Okay, heat, sorry guys, heat is added to system until it reaches 400 degrees Fahrenheit, which we know would be T2. Okay, sorry, this would be given in the problem. You wouldn't just know what temperature it's supposed to add. I just forgot to add it. Okay, here. Okay, so we know that at state 2, we have pressure is constant, T is 400, T2 is 400 degrees. And again, we go right back to our tables, assume a two-phase mixture at table A3E at 60 psi. T is greater than Tsat. So according to flowchart, it is a superheated vapor. And so then we go to the superheated vapor tables, A4E, and then at 60 psi and 400 degrees Fahrenheit, we know that V2 equals 8.35 feet cubed pound. And this is the specific volume at state 2, right? Specific volume at state 2. Okay. So this is why all of that was important. So now we have everything we need for 1 to 2. Why? Because let's go back to that formula. Where is it? I think it's right here. Okay. Okay, so again, we started out with the formula that we had. We started trying to see what we had or what we could get and kind of modifying that formula for usable information. We got to here, we knew that, well, hey, if we can just get specific volume here, we know pressure is constant, we know mass, then we can come down here and fill it all in. So we know pressure, we know mass, and we have just found the specific volume at state 2 and state 1. So I know it seems like a lot, and it is. I'm not going to say that it's not a lot of steps, but you guys have been doing these steps in small increments, and so now you're just needing to apply them. Let's just do another page. Okay, so let's pull over our formula. PV2 minus V1, we're just going to plug in 10 pound mass, 60 pound force per square inch. And we need to get this in homogeneous units. Squared over 1 foot squared. And then times, remember, our V2, which is 8.35 feet cubed over pound, minus 7.485 feet cubed over pound. And then this just computes to 74995.2 feet, pound force times feet. Okay, here's that answer. So not a bad. Okay, so the next example that we're going to run through is a polytropic process example. And so let's start with the given, which is 1 kilogram of an ideal gas with R equals 4 kilojoules over kilograms Kelvin. And that is initially at P equals 500 kilopascals and T equals 800 Kelvin. It undergoes a polytropic process with N equals 1.5 until the final pressure is 125 kilopascals. And we need to find final temp, find work, and show on PV diagram. Okay. And then here's where we work our solution. Okay, so for this one, we can use PVN equals C. A really good hint to this is, again, it has polytropic process, it has ideal gas, it gives you a figure for N. So that all kind of helps you determine what you can use. And so then we will take this, go to this formula, equals C, and then we know again that ideal gas equals PV equals MRT. And so why would we use this? I mean, it does say ideal gas, but why would we use this? We use this formula just to show you the rationale, because we have P, M, R, and T. So it's easy to find V. Okay, so we have these formulas, but we want to use this one because this is going to get us there the quickest. Okay, so let's go with, let's just get a new page. Okay, so at state 1, remember, because we're looking for final temperature, final work, and to show on a PV diagram. So we need to start at state 1, get all of our data here, and then use that to find our final state. Okay? And our formula again that we just said that we were going to use for state 1, that's why all of those are denoted 1s, goes to V equals MRT over P, because this is the stuff that we have and we're looking for volume. And so then we can just plug in. We've got 1 kilogram, 4 kilojoules over kilogram Kelvin, and then 800 Kelvin to 500 kilopascals. So then we're just going to cancel out. Okay, so this is what we're left with. We're left with joules over pascals, and then I'm going to skip the conversion because I know you guys have had a lot of practice with that, but we end up with 6.4 meters cubed. So actually, now that I think about it, I'll just kind of show you this really quick. Let's see. Okay, oh good, so we can see it here. So we end up with the joules over pascals, so we can come over here. 1 joule equals Newton times meter, so N times N, N times M over, and then our Pascal right here is N divided by M squared. n divided by m squared. And then again, this, when you just go to solve this, times the reciprocal, n cancels out, equals m cubed. Okay, so then that comes here. So that's your conversion. And all of those were 1-to-1. So you would just convert it and then put that at the end. Okay, just wanted to show you guys that, just in case you had any trouble. Okay, so we have that. We have the volume at state 1. So now we've got P1, V1, N equals C, right? So we've got our formulas. We moved one over, and now we're going to use this one because we have PV. Okay. And so now we're just going to plug in 500 kilopascals times 6.4 meters cubed. And then our N is 1.5 equals, and then this works out to 0.4 kilojoules. And then since P1 equals P2, V2, N equals C, right? Because we know that P1, V1, N equals C, then we know that this also equals C. Sorry, this was actually 8. Not sure why I put 9. It's most definitely 8. Okay. So since we know that, then we can just plug in, right? Okay, so let's drop down. Yep. All right, so we need to get it in the right order so that we're solving for volume at state 2. And then 1 over n. And then that, when you plug in 4 kilojoules over 125 kilopascals, 1 over 1.5, this V2 equals 16.126 meters cubed. Okay, so now we've got the volume at both states. Let's plug in for T2. What is T2? We can just use the PV equals MRT and then just isolate the temperature. And then let's plug in. And then when you solve this, you end up with 503.97 Kelvin. Okay, so that's the first thing that it asked for. And then the second thing that it asked for was find work. We can do it on the bottom of this page. It's pretty short because now we've, pretty much solved for everything. So work 1 to 2 equals P2 V2 minus P1 V1 over negative n plus 1. This was given in the lecture. So now we're just going to plug in everything that we were given and everything that we have found. Okay, so work 1 to 2 equals 2370 kilojoules. So that is work. Really easy to find once you spent all that time finding everything else. And so now we need to show it on a PV diagram. Okay, so I'm going to pull up another page for this. Also, just to let you guys know, I am in the middle of grading homeworks and tests. I just started looking at the test also to just kind of gauge how you guys are doing. And I know that there was 100. It was actually the first one that I graded. So just to let you know, that it's looking good, but I will say that I'm having trouble giving some people partial credit when you're not putting all of the details on your PV diagram, or even giving full credit, right? Because I want you to show it on the diagram, but you're drawing an incomplete diagram. So make sure that when you're moving over to this, you're drawing the complete diagram. Okay, so remember, well, this is looking a little rough. It's not linear, so, and that did look linear. Okay. Okay, that's better. All right, so we've got a PV diagram, and we know that the area under the curve is work, and we know that this is not linear. So you could have drawn it like this, you could have drawn it, you know, that, however you wanted to. But basically, don't draw a straight line because it's not linear. Whoa, it's not linear. And the area under this curve right here, so in between your state 1, which we know has a pressure of 500 kilopascals and a volume of 6.4 meters cubed. And then we know at state 2, our volume is 125 kilopascals, and we have a volume of 16.126 meters cubed again. So we know that the area under the curve between states 1 and 2, let's go ahead and color this all in. This, wow. Do I have an undo button? Yes. Okay. This is work. All of the shaded in stuff right here. Right? So the example that I wanted to give about drawing an incomplete diagram is if you, okay, so this is the solution, right? I want to give you an example of a not correct solution. Okay, so a not correct solution would just be doing this. That, or this. Even though it's the same kind of stuff, you're not telling me anything. If you don't give me anything over here, that's incorrect. If you're not telling me what state you're at, it's incorrect. If you're not telling me that you understand that everything under here is work, that's incorrect. If this is a line, right? So if your state 1 to state 2 is this, that's wrong. It's not linear. So just make sure I got some examples, not to call anyone out, but that it just looked like this. Or it looked like this and it had like 2 dots here, but you didn't, or like a dot right here and a dot right here, but you didn't draw any bars, you know, so you didn't show that it was on the same bar, or, you know, you just didn't give enough information, or some left out the dome completely. But that's important to show because everything under here is a 2-phase mixture, so it helps identify your mixture and your state and all of that information. So be sure to draw it in its entirety so that you can get full credit. And then also, if you're not really sure, you know, draw what you can on here. Draw a PV diagram for work and label everything. At least let me understand something that, you know, hey, you may not know what the answer is, but you at least know what a PV diagram is. You know, that is helpful. Okay. Okay, so now that we know this, let's move on to some just more, well, general examples, but not so much specifically, you know, with given, find, and solve, right? So where you have to pick out the information. So the example, a 2-meter squared window has a surface temperature of 15 degrees Celsius, and the outside wind is blowing air at 2 degrees Celsius across it with a convection. Remember, we studied this in the lecture. We introduced that. Heat transfer coefficient of H equals 125 watts meter cubed Kelvin. Okay, so that's the question. I'm sure you're reading that like, wow, your lecture didn't look anything like that. Well, that's why we're working it. There's really no way, in my opinion, for you to really get this unless you really understand what we're working. So we need to find the total heat transfer loss. Okay, and so we know that from loss, right? So we're losing, so it's negative heat transfer loss, negative heat transfer. We know that from there, Q is going to be less than 0, right? So we can derive that. So let's work on our solution. Okay, and our power Q convection equals H A times T surroundings minus T system. So that's our formula that was given in the lecture. And then we know T equals, well, we've got Celsius, but let's get it to Kelvin because we've got Kelvin here. Okay, so we've got 15 degrees Celsius, which goes to 288 Kelvin, and that's got 2 degrees Celsius, and that goes to 275 Kelvin. Okay, and so let's go ahead and pull in for this, right? So we know what H is, it's given right here. 5 watts over meter squared Kelvin. Okay, and then times A. What is A? Right here, 2 meters cubed. Okay, and then we have T of the surroundings. Let's go back and note this just in case. And then this is the system. Right, because the wind is blowing at 2 degrees Celsius, so we know that that's going to be our surroundings. So let's put that in, 275 Kelvin minus, and then our T system is 288 Kelvin. Right, and so now we have homogeneous units because we put that Celsius into Kelvin here to match this formula. And then we end up with negative 325 watts, or we can do 3.25 kilowatts, right? Okay. So really easy example right here. So I know that probably when you read that, you were like, I don't even know where to start. But when you see that you have all of the information in this problem in particular, it is really easy to solve. I usually can't solve them on one page. All right, let's do another, just for good measure. Let's do Actually, no, let's do a work. Okay. Okay, I'll pause it and then just write. Okay, so here's the question. It's a piston cylinder device initially contains 0.4 meters cubed of air at 100 kilopascals in 80 degrees Celsius. The air is now compressed to 0.1 meters cubed in such way that the temperature inside the cylinder remains constant. So there's two things that I want you guys to notice right off the bat. Number one, of course, it says temperature is constant. So we know that T1 equals T2, and we know that all that equals 80 degrees Celsius because it says right here it initially contains at 80 degrees Celsius and it's constant temperature. So we know this. So this is something that we've derived. And then right here is air. And what do we know about air? Air is an ideal gas. So I want you guys to take a moment and read your questions and pick out, ask yourself, maybe even write them down, what is my substance? What do I know about it? What is my temperature? What do I know about it? What's my volume? What do I know about it? Things like that. Even if you have to have a check-off list to make sure that you've thought about everything because you're going to need this information to solve it. And it probably is not going to be spelled out for you. So here's the solution. I don't even know what that is, but well, we'll work with it. Okay, so again, because it's an ideal gas and constant temp, we use this formula. And N equals 1. And this is an isothermal process, right? Because constant temp. So that'll help. And then, since we know that now we're using the case of an ideal gas plus an isothermal process, but we're trying to find work, right? So we've got also this formula. And why would we use this one instead of W equals MRT? Well, I'll write that down just so that you understand. So we use this one instead of the ideal gas one for work. Why? Because we weren't given mass, right? So we're using the one that we can solve. We weren't given mass, so we can't solve it. And eventually, if you did start off trying to use this one first, you would eventually get there because you wouldn't be able to solve it. Or it would be taking a copious amount of time because you're out trying to find data when there's one that can get you a lot quicker. Okay, so let's take our formula. And start plugging in. Okay, and then when we work all of that, it is okay. And what do we know from this negative right here? We know, so what do we know about a negative work, guys? Negative, so we know work is being done, what, to the surroundings or on the system? On the system. Okay, so we have this one. Let's go on one that's a little bit more tricky. I'll pause. Okay, so the question here is consider a two-part process with an expansion from 0.1 meters cubed to 0.2 meters cubed at a constant pressure of 150 kilopascals, followed by an expansion from 0.2 meters cubed to 0.4 meters cubed with a linearly rising pressure from 150 kilopascals to 300 kilopascals. Find, and we need to show the process on a PV, and work, which is boundary work. All right, so let's just do this PV here real quick, and then we'll go to another page to actually solve for work. Okay. We know PV. Right, okay. So first we know our volume, which is 0.1, 1 meters cubed. And then we know that it goes to 0.2. And then it's followed by an expansion from 0.2 to 0.4. So 0.2 to, we'll just say this is about 0.4. Okay, so we've got our digits for that. And then what's our pressure looking like? We've got 150 to 300. So let's just do 150 here and about 300 here. Okay, and so we know that consider a two-part process with an expansion from 0.1 to 0.2 at a constant pressure of 150. So 0.1 to 0.2 at a constant pressure of 150. So we know that that's going to look about like that, right? Okay. And so then followed by an expansion from 0.2 to 0.4 with a linearly rising pressure from 150 to 300. So we know that we're going from here to here and then up to here. And we know that this is linear, so I'm going to do that as very straight as I can. Okay. Okay. So this is a two-part process, right? So we went here to constant pressure, and then we expanded. And then what do we know about what's underneath here? Again, we know that it's work, right? So we know that what's under here is work. It's a two-part process, So this is our first part, and then this is our second part, okay? So we know that this is work. And when does this work? 1 to 2. And then we have some more work. Ooh, let's do rainbow pen. And then what kind of work is this? This is work 2 to 3. Okay, know that we can use this formula and we can solve for volume solve using the integral from volume at state 1 to 2, P, D, V, right? Because we use this a ton. What do we know? We know that pressure is constant. Why do we know that pressure is constant between 1 and 2? Because it's right here. I mean, it says it right here too, but you can clearly see it from here. And this is what we're solving for. So what can we do? We can pull this out in front. And then when we solve the integral, it ends up looking a lot like this, equals P V2 minus V1. Okay, so let's go ahead and plug in for this because we have a lot of this data. So we've got our constant pressure of 150 kilopascals, and then we've got V2 minus V1, V2 minus V1. And that equals 15 kilojoules. Okay, so that's our work here between 1 and 2. And then we'll do the same thing for work 2 to 3. And let's see, we'll just continue. We'll just do it again, just so that you guys can see it again. PDV, same formula again, but we're doing this for state 2. So where this was P1, this will be P2, V3 minus V2. And then we need to look at the expansion, right? Because right now we're looking a whole lot like this first formula. And this formula was covering the work underneath here. So it wouldn't make sense to use the same exact formula for this work because this work looks like this and this work looks like this. So we need to account for this expansion. So you guys kind of got a little bit of this, well, now we'll do galaxy bin. You guys kind of got a little bit of this on your, I think it was your first assignment, but where you're going to have to split it into things that you know, okay? So we know that we can make this the same shape as over here so that we can use the same formula. So this is going to be sufficient for this. And then we need to use a triangle formula to account for this. And then just add them together. Okay, so what we have right here is this. Okay, so we have this. And then now we just need to add the formula for a triangle. Again, 1/2, which is 1/2, it's going to be the V times the P, right? Because it's just the regular formula for a triangle. So we're going to do that by 3, 2, P3 minus P2. And how would you know this, right? But other than you're trying to get a triangle and you know that you have to use a triangle. But again, we're trying to find work. And work at 1 doesn't exist. Work at 2 doesn't exist. Work at 3 doesn't exist. It only happens with the processes. So look at what we're looking at. We're looking at what's happening in between volume 2 and 3, what's happening in between the pressures of 2 and 3. So that's why you're using this 1/2 and then the difference of volume and pressure. Okay, and so then when you fill this in, 50 kilopascals, 0.4 meters cubed minus 13 meters cubed plus 1/2 0.4 meters cubed minus 0.2 meters. We have work from 1 to 2 and we have work 2 to 3. So what we want to know is what the work is, the boundary work. And so we need the work 1 to 3. And so then that is just really easy, adding them together. 15 kilojoules plus 45 kilojoules equals 60 kilojoules. That is your final answer. Woohoo! Okay, let's do something. Okay, so this one is going to be kind of a long one, and it's going to wrap pretty much everything that we've been doing since the beginning of class into a question. So we've got 2 kilograms of refrigerant 134A undergoes a polytropic process in a piston cylinder assembly from an initial state of saturated vapor 2 bar to a final state of 12 bar, 80 degrees Celsius, and we need to find work between 1 and 2. So what do we know about that right off the bat? It gives us a polytropic process, and we know saturated vapor, right? Initial state of saturated vapor. Okay, so let's start working our solution. So let's start off with our knowns. What do we know? We know we have refrigerant 134A. And we also know that it's not an ideal gas, so we can rule that out. This helps minimize our available formulas to use. What else do we know? We know a polytropic process. And we know that for that we can use PVN equals C. And we do have an unknown N. And then what else do we know? We know at state 1, it's saturated vapor. Okay? And then what else have we been given? Okay. So at state 1, we know that pressure is 2 bar. And we know that we have a quality of 1, right? Because it's saturated vapor. All right, and state 2. What do we know? We have a pressure of 12 bar. And we know that we have a temperature of 80 degrees Celsius. So this is what we know about both of those. And we know that we can use this formula. Know that this one would work. And we know that we can use it as this. And we know V equals M times V. Okay, so we know that we have these formulas. So what do we do? Let's go here. Okay, and so first we need to go to the tables. So from table A11, YA11, let's see, because it's refrigerant 134. And we know that at a pressure bar of 2, we also know that it's saturated vapor, so we can come right over here and pull up our V for saturated vapor. So we know that V1 equals Vg equals 0.0993 meters cubed kilograms. Okay, and then state 2, what else can we do? We can always assume a 2-phase mixture if we don't know what the phase is. Again, table 11, and then at P equals 12 bar and a temperature of 80 degrees Celsius. Csat on the table is 46.30 degrees Celsius. On a superheated vapor. How do we know that? We used the flow chart. And then that table is A12. And so then we will go down to 812. So we're just going to scroll down here. Oops. We're just going to scroll down here and then pick up this V, which is 0.02051 meters cubed kilogram. So our V2 equals 0.02051 meters cubed kilograms. And then now we can go and plug into that formula. Equals C. And then this can go into P1, V1 N equals P2, V2 N, Y because it's constants equals C, P1, V1, 2, V2 N. We have V, we have specific volume V, so that's what we're going to use. Let's get it into something that we can actually use though. 2 over V1 over N. And then now we need to get rid of this N, so we're going to go here. We know we can do the log P1, P2, and then that equals log of V2 over V1 N. Then we know that that all goes to, okay, log P1 P2 equals N times log V2 over V1. Okay, and then you can pull out, move this over and pull out N to finally get log P1 over P2 all over log of V2 over V1. And then just to save space, here you see that we've gotten V1 and V2, so you would just plug those in along with the pressures that we were given. And then when you solve this, you get N equals 1.136. So what do we know about this? We finally got our N. And what do we know? Well, we know that there's a formula for N equals 1, and we know that there's a formula for N does not equal 1. So now we have to go back and get our for N not equal to 1. Right, because we started with our first formula because we knew that we would need N. And now that we know what N is, we know that it differs from 1. What just happened? Do I have to write that again? Did I just? Oh, okay. All right. So we know that it differs for 1, so now we can use this formula. P2, V2 minus P1, V1 over 1 minus N. Again, same formula from the last problem. Minus, but getting it into a way that we can use it. Again, you see that mass coming into play when we're getting it into specific volume. And then we would do into 2 equals, let's just start plugging in, okay? And yeah, let's go ahead and do these conversions as well, just in case, because this one's kind of a big one. Squared over 1 bar. And then, well, I guess it's not really. I just have it in my notes. So I might as well. Okay. And then we've got 0.25205 1 cubed kilograms. Let me make sure that's right. 02051. Yep, okay. Okay, so now we have another question that we're going to use the first law in. So all of the examples prior to this, if you're following along, wondering kind of where we're at in the lecture, when we got to the point in the lecture where we said now we're going to move into the first law formula, and we use the differential, that's kind of where we are now. We're kind of moving into the first law. So we have 2 kilograms of water in a free-moving piston cylinder. It is initially at 300 kilopascals with a quality of 25%. It is heated in an isobaric process until it achieves a 26.4 degrees Celsius temperature increase. Find Q, heat transfer 1 to 2, and work 1 to 2. Okay, so let's look at, you do have some problem solving steps, so I will kind of briefly introduce those two. Oh, okay. State the problem. And this is very helpful because I think in my notes, let me see, actually 1, 2, 3, 4. I mean, I've got like 4 pages here just to solve this one. 5 pages. Okay. So let's state the problem, which we did right here. And then let's do our given and derived information. And so we know that the mass, the water equals 2 kilograms. We know that the pressure at the first state is 300 kilopascals, and we also know that that's 3 bar. And then we know about the quality is 25% or 0.25. We know that state 1 is a 2-phase mixture. Why do we know that? This is derived because we have quality, right? Because quality only occurs under the dome. So we know that state 1 is a 2-phase mixture. We also know that it's isobaric process and that this is constant pressure. So we are given a pressure. P1 equals P2 equals 300 kilopascals or 3 bar. And then we also know that T2 equals T1 plus 26.4 degrees Celsius. And why do we know that? Because it's in a constant pressure process until it achieves a 26.4 degree temperature increase. So we know that this is the difference between T1 and T2. Okay, and then again, what else do we know? Well, we know what we're looking for, right? Because this is going to hugely determine what formulas we use and kind of what direction we go in. So we're looking for Q1 to 2 and work 1 to 2. Okay, so let's pick up another page. So we know that we can use the first law formula, which is change in E equals Q minus SW. And then to get W, we can use work 1 to 2 equals, again, our formula that we've been using for this, PDV, which is boundary work. And why do we know that? Because work occurs at the boundary. We can go to pull out our P, because it's constant. We can pull that out to the front of the integral. dv, which also then goes to P1, and then that is M. So we know that if we need to get it to specific mass basis, we can get it here. And then we'll just plug that in. PM V, well, that's little v. Let me draw it smaller. Even though I won't put a line through it, I'll draw it smaller. Minus V1. E1. Okay, so this is the formula that we end up with to try and get work. What's that one? Really, it's any work. Okay, so let's pull up another page too. This part's going to be kind of long. Okay, so at state 1, what do we do? What do we always do at state 1? That's right. We assume a two-phase mixture. And so why do we do that? Well, we need to get all of this other data. The reason why we start and we just go straight to the tables, if you're still kind of confused about why we do that, and you're just kind of going through the motions of, oh, well, I mean, she tells me to go to the table, so I'll go to the tables. It's because we need this other data, and that's where the tables are. So that's where the data is. It's in the tables. And so again, just like in chapter 1 and 3 that we learned in, that you just start with an assumption. In this case, we actually do know that it's two-phase mixture because we know that we have quality, right? But in any case, we start with the two-phase mixture, and then we use our flow chart, and then we're just getting as much data as we can and as much values as we can so that we can use that data to plug into the very best formula that we can use to get to the answer that we need, right? So that now we're in like the big picture. So we spent the first chapter learning about what thermodynamics is and kind of learning the language. Then we spent chapter 3 learning how to pull all of that data from the tables and working a few small equations. And now we're learning in chapter 2 how to incorporate that into the first law of thermodynamics. Okay, so at state 1, it's a two-phase mixture. Assume a two-phase mixture. It actually is a two-phase mixture because we have quality. Right, and so then we know P1 equals 3 bar because we did that conversion, and a quality of 0.25, table A3, and from table A3 you were able to get V1 equals VF 1 minus X plus X VG, and then V1 equals, now we're just plugging in, okay, and then V1 equals 0.15226 meters cubed kilogram. Okay, and so while we are here, you probably won't know this right now, obviously that's what I'm telling you, but we're going to go ahead and pick up the specific internal heat while we're here because we are going to need it for later. So if you still are kind of unfamiliar, or not so much unfamiliar, but if you're still having trouble in the tables, I mean, I can tell you that I have graded the vast majority of homeworks, and there has been yet for me to receive one of those tables that you guys filled out that was 100% correct. So if you're still struggling to pick up every single thing correctly from the table, you're not alone. Literally everyone else in the class is doing that too. So if you get really comfortable and it takes you a long time to get somewhere, go ahead and write down the stuff that you can find from there. So write down the whole line if you need to, if that is helpful for you. That way, if you find that you need something later, you have it written down. So let's go ahead and find specific internal heat while we are in the tables. We will need it later. That way, if you're coming back, you understand why I wouldn't found it. Okay, so U1 equals UF, 1 minus X plus, this is a formula. Okay, U1 equals 561, 15, 0.25 plus 25, 2543.6. U equals 1056.76 kilojoules, kilogram. And then we also know we can also get our temperature, right? Because we're at the right table. So we know that T1 equals our Tsat, which is on our table, and that's 133.6 degrees Celsius. Okay, so we have this information. We were able to find specific internal heat, and then Tsat, and then specific volume. Okay, perfect. So we found all of this for state 1. Let's go ahead and then find it for state 2. Okay, we know that pressure is constant, remember? 3 bar. Okay, we know that we have a temperature increase, so we know that T2 equals T1 plus 26.4 degrees Celsius. And we found our T1, which is 133.6 degrees Celsius plus 26.4 degrees Celsius, which ends up being 60 degrees Celsius. And then what can we do here? Again, we can assume a two-phase mixture. Why? Because we were only given the phase, the state of this state 1, not state 2. So we can do at table A3, we have a pressure of 3 bar, and we have our temperature, which is 160. What we end up finding is that our Tsat is about 133.6, remember? Because that's actually what we pulled from the table. So we know right off the bat that that's larger than the Tsat. And then we will go to, per our flowchart, we will go to superheated vapor tables. Okay, and I'll even put from flowchart. If you're having trouble getting through these steps on your own, because this is, you've been doing small parts of these throughout the semester. So if you're having trouble combining all of them, write down the steps and keep them with you so that when you start working through the homeworks and through the practice exams and things like that, you have kind of like a roadmap to go on. Okay, and so from this superheated table, at P2 equals 3 bar, which was our constant pressure, and a T2 of 160 degrees Celsius, which we were able to find out, we know that V2 equals 0.651 meters cubed kilograms, and we'll also find U, 2587.1 kilojoules kilograms. And do not forget your units, guys. Units. This has actually been the very best semester with remembering units. I'm so impressed. It really is usually a just huge issue. It has been so nice to see this. Glad to see that it's not a broken record. But I'm still going to keep going so that you guys still keep doing a good job of that. Okay. So let's move over here. And we know that, well, I better just pick up another page. Okay. So again, what's our work formula? We wrote it on the first page, but we got PM over, did it again, small v. V2 minus V1. And then we've got work 1 to 2. And then we've got 300 kilopascals, 2 kilograms. Remember that was given, 651 meters cubed kilogram minus 0.7522 meters cubed kilogram. And then all of that equals 299.25 kilograms. Okay, so that's your answer. And then what do we know about this? It's positive. So the work is an expansion and done by the system. Okay, so that's what we know. Sometimes you'll be asked that, sometimes you won't. Okay, so that is the end of that question. A piston cylinder initially contains 0.5 meters cubed nitrogen gas at 400 kilopascals and 27 degrees Celsius. An electric heater within the device is turned on. It is allowed to pass current of 2 amps for 5 minutes from 120 volt source. Nitrogen expands at constant pressure and a heat loss of 2800 joules occurs during the process. Determine the final temperature of nitrogen. Okay, so what do we know? We'll just put known here. Okay, so we know that nitrogen is an ideal gas. Whoop. So we know that right off the bat. I always want that to kind of come as a red flag because we know that ideal gases are special circumstances in special situations. So it's going to narrow down your window of available formulas. So that will also help. We know that we have a volume of 0.5 meters cubed. We also know that we have a pressure of 400 kilopascals. And we have temperature. Goes 27 degrees Celsius. Let's go ahead and put that into Kelvin. 300 Kelvin. Okay. And we know that we have an electric heater. And that within that electric heater, we have a current of 2 amps. We know that our volts is 120. We have a change in time, right? Because it happened for 5 minutes. And we know what the heat transfer loss is, right? Because it told us. And it's a negative because it was a loss, right? So negative because of loss. And let's see. Okay, so how can we find out these formulas? So how about how to tailor formulas? Okay. So we know that we have the first law formula. Oh my gosh. I thought that I would like get a lot better at this, the more that I did this, but I don't know. I like to think it's improving. Okay, so first law equals dE equals QW. Okay. And so we know again that we can break this down. What do we know about total energy? Well, we know that total energy is the change in kinetic energy plus the change in potential energy plus the change in internal energy, right? So we can put that all equal. And then let's look at it. Have we had any kind of mention of velocity? No mention of velocity. So we can omit this. Omit because no mention of velocity. And just to clarify, it's not so much that we're omitting it, like we're just taking it out. What it is that we're assuming that it's zero. And so then kinetic energy would be zero, and of course, thus the change in kinetic energy would be zero. And then when you're adding zero to your equation, it's nothing, so we can omit it. And then again, what else can we do? Well, we know that potential energy is based on elevation change, which there was no mention of, so we can omit this. Omit because no mention in elevation change. Right? Okay. So then what we're really left with is du equals qw. Okay. So that's really what we are left with. And then we can rewrite the change in u as u2 minus u1, right? And let's see, we can do this also. We can write this inexact differential. It's Q1 to Q2, and then we can write this one as well as W1 to 2. But what else do we have to include? Because we have another type of work, right? Because remember we covered that there's different types of work. So we've got, positive work, positive and negative work depending on if it's being done by or on the system. Well, we also have electrical work, right? So we need to also deduct the electrical work. Okay, and so now I'm going to pick up a new page because that's our formula. All right, and so now what do we need to find? We need to find the electrical work. And what's that formula? Go. Let's change T. We've got all this. Remember, we wrote it down in our notes. So we're just going to plug it in. 2 amps times 120 volts, 5 minutes. And let's go ahead and convert that into seconds. Which ends up being electrical work of negative 72,000 joules or negative 72 kilojoules. Okay, so we've got the electrical work there. Now let's look for the boundary work. Okay, and what is that formula? We've been using it. This is like the third or fourth time. PDV. And again, we can break this down we can pull out P and then solve for the rest of the integral. And what we end up with is P V2 minus V1. Okay? And so then we can plug this into our previous formula, which remember was U2 minus U1 equals Q12 minus W12 minus work of the electricity. So let's go ahead and just rewrite this down, but plugging in this, this for work 1 and 2. This is where work 1 and 2 would go, but we're just going to drop that down. And then this is where that would go, even though we have that. And what do we know about H? So we know H equals U plus PV. And so then what we can do is we can remove this and start taking some of these out to start to simplify our formula. So what this is going to go into is H2 minus H1 equals Q 1 to 2 minus WE. And then if we wanted to go to specific, so mass base, then we would end up with M H1 minus, right, because we would just pull the mass out. Actually, it's H2 minus H1 equals Q2 WE. Okay. And so what do we know about nitrogen? Because that's our substance that we're working with. We know that it's an ideal gas. So for ideal gas, we know that H2 minus H1 equals Cp, T2 minus T1. And so then we know that this can go into here. It's T1 equals Q2 minus W. So I accidentally just stopped recording and finished the problem. So I'm going to try and kind of pick up where I left off. But basically it was the ideal gas law, and then we saw how we substituted in, but we are going to now use, let's see, MCP T2 minus T1 equals Q1 to 2 minus electrical work. And we don't know this, right? But we know this. We know this. And we know this. Okay, so we don't know this and we know the rest of this. But what do we know about all of this? Well, we know that we can find this from tables. And we know that we can use the ideal gas law for this. So let's just use the ideal gas law first. And that will be PV equals MRT, but we're just going to move it to isolate M because that's what we want to find. Over RT1 equals, and when we plug all of that in, 2.246 kilograms. So now we know this. And then we can find that from the tables, which is CP. It can come from table A20, and that is 1.039 kilojoules, kilogram, Kelvin. And because we only have one temperature, right? So because we only have one temperature, we're not going to average them together. Remember in the lecture, I said, hey, if you have both of them, you average them together. But if you have one and not the other, you just use that one. So that's what we're doing here. We're just using T1. So let's go ahead and get an equation going and isolate it for T2, right? So let's move everything over and take this equation to T2 equals Q1 to 2 minus electrical work MCP plus T1, right? So we end up just dividing this to move it over here and then just adding the T1 to get it over to this side. So this is our formula right here, because this is also what we're trying to find, right? T2, that was what was asked. So then we're just going to put in, remember our 2800 is negative because it's a negative heat loss, minus a negative 72,000 joules over 2.2466 kilograms, 1.039 times 10 to the third grams, kilogram Kelvin, plus 300 Kelvin, which ends up being 329 Kelvin or 57 Celsius. Okay, so that's our answer. Let me make sure I'm recording. Okay, yeah. It'll pull up. Okay. Okay. So example, it's a system consisting of 2 kilograms of ammonia and it undergoes a cycle composed of the following processes: 1 to 2, 2 to 3, 3 to 4. And then it has some information, constant volume from P1, which is 10 bar. And then we've got a quality to saturated vapor, constant temperature, isobaric process. And again, we got a cycle, so we know it goes 1 to 2, 2 to 3, 3 to 4, and then 4 to 1. Because that makes that whole cycle. And then sketch a PV and TV diagrams, determine the net work for the cycle, and the heat transfer for each process. Okay, and what else do we know? So we know that, first of all, we already have enough information to find the state here. So we have enough info to find state. Okay? So we know that we have enough information to find the state. We need 2 independent intensive properties. And for this, we know that right here that this is a positive, right? So we know that this is a positive heat transfer. Which means the system is gaining heat. And then isobaric process, we know that it's constant pressure. Oh, sorry, this is 3 to 1. Sorry about that. So we know that P3 equals P1. Okay. So that's the stuff that we were able to be given or derived. So let's look at the solution. We've already kind of started working on the solutions with finding out what the given and restating the problem, things like that. Our substance, what is our substance? It's ammonia. Okay. And how do we go about finding out which formula that we need to use? So we know that if the heat is not, I'll even just write this down. If heat is not conduction, convection, or adhesion, the heat must come, dang it, come from the first law. Right, so that's good to know. Because if it's conduction, if it's convection or adhesion, you would use those. And if it doesn't come from any of those, then it must come from the first law, which we use a lot of because that's what we're covering. Okay. So let's pull up another page. So because of that, therefore, process 1 to 2 with the first law. I'll just rewrite this again. And again, what do we know about this first law? We know that we can break it down to kinetic energy, potential energy, and internal energy. Well, we know that there's no mention of velocity, so we're going to not include kinetic energy. We also know that there's no mention of elevation change, so we're not going to include potential energy. So this is going to just be derived into du equals with W. And then we know that we can derive this even further because it's a change in U, that this is U1, U2 minus U1 equals 2 minus 1 to 2 work. Right? Okay, and so what kind of assumptions did we make? So we need to write our assumptions. So be sure that when you're writing on your test, when you just assume that there's no PE and assume that there's no KE, don't just also assume that I know that you're doing it for a reason, because there's oftentimes that there's a lot of information left off, and that's why you get it wrong. So make your assumptions so that I know that you know what you're doing. And it can be just as easy as change in KE equals change in PE equals 0, right? So now I'm going to know that you just omitted that to 0. We also know that there is no mention of change in volume. So we're going to assume that the boundary work is what we need to be looking at. So let's put the boundary work formula. Right. So no mention there. So we're just going to assume that it's 0. And let's see. And then volume, the change in volume is going to be 0 because we have a constant volume. Okay, so these are the things that we have made assumptions on. And so you could write them down just like that, but just be sure to make note of them. Okay, So now what can we do? Well, we can change it into a mass basis, right? So these are supposed to be like copper, right? You can't tell. Okay. So we can change these into a mass basis. So let's pull the mass out. Right, because we just assumed that this was 0. So we're now just Xing that up. Okay, and we're looking for this right now. Well, it's unknown. So where can we get this? From tables A14, two-phase mixture, ammonia, P1 equals 10 bar, and X1 equals 0.6. And so then we know that from that we are at state 1 of a two-phase mixture. And so then what we can do is just start plugging in, because now we can get all of our data as far as specific volume and specific internal energy. So let's go ahead and just find those. Again, just like we did in the last problem, or really now it feels like so many problems ago because I had no clue that I wasn't recording. 1.6584 times third. .285, and then this ends up being 0.0777 meters cubed kilogram. And then we're going to do the same thing for specific internal energy. We're going to use that formula. Okay. And plus 0.6134.66. And that goes for 919.24 kilojoules kilogram. The next page to get my state 2 data. So now we will go to state 2. And we know that that's a saturated vapor. And because of that, we know that the quality is 1. And we also know that volume is constant. And on this, you would have to interpolate. So I got this from the table. So value is located between 10 bar and 14 bar. On table A25. Therefore, we interpolate. Okay. And so A14. Okay. So we have V equals. This might be the only one that I actually work out the entire interpolation. It's pretty easy, and I know you guys have done enough examples of them, and have seen me work through enough examples of them. So this will probably be the last one that I fully work out. There should be plenty of material now if you need to see many examples. 97 kilojoules kilogram. This will be the same units going down, so I'll just draw a line that way I know what it is. 1941.88. Okay, and so then I can take this and plug it into the formula. Okay, and then U2 ends up being 1341.27 kilojoules kilogram. Okay, and so then we're going to go back to our formula because now we have this data that we can plug in and get the heat transfer between 1 and 2. So we've got that, and then we plug in 2 kilograms, 1341.27, whoops, minus 919.24 kilojoules kilogram, and then Q 1 to 2 equals 844.07 kilojoules. And so what do we know again about heat transfer? This is positive. Therefore, we know it is added heat during this process. Okay, so for process 2 to 3, you can use first law again, which is change in total energy equals quality of heat transfer and work. Again, could break it down, but we know that we already wrote our assumptions as PE and KU being 0. So that's going to go to a change in U, Q minus W, and then we can break this down to U3 minus U2, Q2 to 3 minus work 2 to 3, and then M, because we're going to get this into specific internal energy because that's what we can find from the tables. Q2, 3. So just getting the formula to what we can work with. This is given. Found in tables, right? Because we already found that. And that is, we have this now because we solved for this. And now we don't have that. Okay. So at state 2, we have saturated vapor. That has a quality of 1. And we know, again, constant volumes equals 0.777 kilogram. And then, again, table A14, we would do linear interpolation. If you need me to run through this, send me an email. I have it. I just am not going to write it down again if no one else needs it, because then it's just kind of a waste of your time. And then what else? So we know that the problem gave us the fact that T2 equals T3. for state 3. So therefore, at state 3, we know T2 equals T3 equals 42.48 degrees Celsius. And we also know that at state 3, when we're making that cycle back around, right? So here's our cycle, got 1, 2, 3, and then it's this cycle, right? And it's at a constant pressure back. So we've got P3 equals P1 equals 10 bar, and that was given. So we are going to assume a two-phase mixture because we need some more data. And that table is A14. And our temp is between 40 and 50. We must interpolate. Okay, and then that ends up being 0.1402 kilograms. Okay, so now we have that. So because we need U3 later on, let's go ahead and find it. Again, you're going to have to find, you're going to have to interpolate again. So let's find U3 while we're here. As you know, there's so many tables. So while I'm working in the tables, I like to just get as much data as I can from there, so that I don't have to go back into it and, kind of go through the whole thing again. Let's find 3 while we're here. Okay. And so then we have to interpolate, which ends up being U3 equals 1374.88 kilojoules kilogram. Okay. So now that we have all of this data, we can finally plug it into our work formula between 2 and 3. 2 and 3 minus M U3 minus U2. See, we need to get that. Okay, so when you plug all of that in, you get, I'll plug it in just in case. 74.88 kilojoules kilogram minus, whoops, that's supposed to go in the parentheses. Okay. Minus 1348.27 kilojoules kilogram. And then that works out to be 160.81 kilojoules. Whoa. Okay. And so then now we need to get the process from 3 to 1, right? So we've got all that. Now we need the process from 3 to 1. And what are we going to do? We're going to apply the first law. Because it didn't say that the heat came from anything other than that. So we're, again, kind of assuming that it comes from the first law, because if it doesn't specifically state that it came from things like convection and so on, adhesion, then it must come from here. So again, change in total energy. And then we again know potential energy, know kinetic energy, and we know that we can derive the change in U as U2 minus U1, but that U2 minus U1 in this case is going to be U1 minus U3. 3 to 1 minus work. Oh, 3 to 1. Okay. And so then we can pull, gosh, I did it again. Okay. Then we can pull the mass out. Okay. And we already have this. We don't know this. And we don't know this. But we can find this. Okay, and how do we find this? Well, we know that work equals PDV, and then no exception to this. Let's do our volumes, PDV. And then we know that we can pull, all right, and so we know that we can pull P out, and we can also take out mass when we're talking about these total volumes here. So this is going to end up with, once we do both of those steps, it's going to end up with a constant mass being pulled out. There you go. Okay, so this is the formula for that. And now we can solve for it. So let's do 3 to 1 equals PM V1 minus V3. And then when you plug all of that in, you're going to end up with negative 124.97 kilojoules. And that is negative work. Okay. So, and just a note on this, this first is a kilopascal, or it was 10 bar, but we converted it to homogeneous units, so we did kilopascals. So just note that I have also skipped that step in working it out here. So then let's go now to this formula right here that we've got. And let's isolate heat transfer, because now we have work 3 to 1, so we can plug this in. Now let's isolate heat transfer. So we've got Q 3 to 1 equals M U1 minus U3 plus W 3 to 1. We're going to plug all of this in, and we're going to get negative 1036.23 kilojoules. And this is negative. So heat transfer is leaving the system. Okay. And then what else do we need to find out? Well, we need to find out what the net work is, right? Which is just all of them added up. Okay, and so then again, we're just going to plug in, because now we found all of these. So 0, 160.81 kilojoules plus negative 124.97 kilojoules. Okay, and so then our net work ends up being 35.85 kilojoules, and we ended up having an overall positive work through all processes. Okay, so why is this important? Well, because we just found out right here. Okay. Because right over here from processes 3 to 1 that we had a negative work. But overall, our entire cycle has a positive work. So that's really important. And then lastly, we need to draw them on a TV and PV diagram. TV, oh, that needs to be longer. Okay. And then we have a PV. So we know that we have 2 constant pressure bars here. Okay, and we know that we had a constant volume. And we know that we had constant temp. Okay, so all of this is our first process. And let's denote our cycle. Let's do it in black. Okay, so we've got state 1, we've got state 2, and we've got state 3. And so we know that it goes up from state 1, it goes over from state 2 to 3, and then it goes down and over from state 3 to 1. So that's how that looks on a graph. All right, and so let's do the same thing over here. Okay. All right, so now, again, we have constant volume right here and constant pressure. Okay, let's use a galaxy pen. Okay, and so right here is where our process or our cycle 1 to 2, 2 to 3, and 3 to 1 is. And then this is it just represented on the PV and TV diagram. Okay, I definitely love the galaxy pen. If just literally anyone wanted to know, just love it. So again, we've got state 1, state 2, and state 3. And this is their like track, if you will. So we've got to go in this way. Well, that's not good. And then we've got to go in this way. And then we've got to go in this way. So that's how it looks going up and around for the cycle.